So imagine you're writing a piece of Python code. It solves this massively complex network optimization problem, and it does it flawlessly.
Right. It feels like absolute magic when you're writing it.
Exactly. It's utilizing thousands of parallel processing threads, crunching all the numbers perfectly. Everything is great, right up until you deploy to a server that just happens to be missing a dedicated graphics card.
Yeah. And we all know how that story ends.
Oh, yeah. Instead of adapting, the entire program just instantly self destructs. It throws a hard runtime error and dies on the spot.
Which is, I mean, that's a terrifying outcome if that code is managing a critical piece of infrastructure or, a massive data pipeline.
Totally.
The safety nets of high-level programming languages suddenly turn into this incredibly tight straitjacket.
Yeah. And today we are looking at an absolute masterclass in breaking out of that straitjacket.
Yeah.
We're doing a deep dive into a fascinating 2026 technical breakdown. It's by a developer who goes by the handle at LUK036.
Yeah, Luck036. The post is titled Accelerated Vertex Cover, Porting Python CUDA to C++.
Right. And our mission today for this deep dive is to explore exactly how bridging the gap between high-level Python and bare metal C++ on a graphics card, a GPU massively accelerates problem solving. We're going to unpack all the agonizing engineering hurdles required to make a CPU and a GPU actually talk to each other without, crashing the whole system.
It really is a perfect case study. It shows what happens when you stop politely asking the computer to do something and you start directly commanding the physical architecture. It requires stripping away all those comfortable abstractions and really getting down to the raw silicon.
Okay, let's unpack this. Yeah. Because before we even look at the massive code rescue mission this developer undertook, we need to understand the actual mathematical puzzle they were trying to solve in the first place.
Right, the algorithm itself.
Exactly. The challenge centers on Pitt's randomized algorithm for the vertex cover problem.
Yeah, and vertex cover is, well, it's a foundational puzzle in network optimization. The core objective is finding the absolute most efficient way to monitor every single connection in a network, every edge, basically.
Let's visualize this for everyone listening. Imagine you were tasked with placing security cameras at street intersections in this massive city, and your mandate is to watch every single road.
Right. No blind spots allowed.
None.
Right.
But here's the catch. Some intersections are dramatically cheaper to install cameras at than others.
Yeah, like maybe one intersection already has all the electrical wiring ready to go.
Exactly. So it costs a fraction of the price of an intersection where you have to, dig up the concrete and lay new pipe. So you have to cover every street, but you need to spend the absolute minimum amount of money.
And in Pitt's algorithm, every time it evaluates a street, let's call it an uncovered edge between two intersections, point U and point V, it forces a choice. Where does the camera go? But the math here relies on a probability formula. It doesn't just default to the cheaper option every time. It picks an intersection with a probability inversely proportional to its cost.
Okay, wait, let's put numbers to that. Say intersection U cost $100 to wire up.
Okay.
And intersection V costs $300. The probability of picking intersection U is the cost of V divided by the combined cost of both.
Right, so 300 divided by 400.
Exactly. You have a 75% chance of picking the cheaper $100 intersection and a 25% chance of picking the expensive $300 one. So lighter, cheaper vertices are mathematically weighted to be selected more often.
Precisely.
But wait, if we have the master blueprint right, we know the exact cost of every single intersection in the entire city. Why are we rolling the dice?
That is the big question.
Why use a Monte Carlo method relying on randomness instead of just locking in the absolute cheapest option every single time? I mean, that feels like a massive step backward in logic to me.
Well, greedy algorithms, the ones programmed to relentlessly grab the cheapest immediate option, they frequently paint themselves into corners.
Oh, I see.
Yeah, because grabbing the cheapest intersection right now might actually force you to install cameras at, say, 5 incredibly expensive intersections down the line just to cover the remaining blind spot.
Because you didn't plan ahead.
Exactly. So by introducing this weighted randomness, Pitt's algorithm naturally avoids those local traps. It guarantees a 2 approximation in expectation.
Meaning what, exactly?
Meaning your final cost will never, on average, exceed twice the absolute mathematically perfect ideal scenario.
Oh, wow. That's actually pretty solid. And there is also a post-processing phase, right, to sort of clean up the mess.
Yeah, the reverse delete step.
Right, a reverse delete step. So once the initial randomized map is laid out, the algorithm sweeps back through the city and checks every single camera. It asks, hey, if I remove this camera, does any street go completely blind?
And if the answer is no, it just unplugs the redundant camera. It tightens the efficiency of the whole grid.
But the randomness of that initial phase, that is the key to unlocking the hardware acceleration, isn't it?
It is. It relies entirely on the concept of trivially parallel trials.
Okay, unpack that.
Because the camera placement decisions are dictated by weighted dice rolls, no two attempts to map the city actually depend on each other.
So you aren't just solving the puzzle once, you are running thousands of parallel universes simultaneously.
Exactly.
You simulate out 10,000 independent maps of the city, you run the reverse delete sweep on all of them, and then you just pluck the single cheapest map from the pile at the end.
And that's why you need a GPU, because a standard CPU with, I don't know, 8 or 16 cores, it would just choke trying to run 10,000 independent simulations.
Right.
But a GPU houses thousands of incredibly fast, specialized cores. You can dedicate one entire city simulation to a single CUDA thread on the graphics card and run them all at the exact same time.
So if a GPU gives us thousands of parallel roulette wheels to run this math,
Mm-hmm.
why did this developer's perfectly good Python code suddenly become such a huge liability?
Well, let's look at how it was built.
Yeah, the original baseline was built entirely in Python, utilizing a tool called Numba and a decorator called at CUDA.jit.
Right. Numba essentially acts as an automatic translator. It takes this highly readable Python code and auto-compiles it into PTX.
Which is what, for those who might not know.
It's essentially a pseudo-assembly language designed specifically for NVIDIA chips. The GPU driver then takes that PTX code and compiles it just in time for the specific hardware you're running.
And Numba was also taking standard Python NumPy arrays and automatically mapping them into CUDA memory pointers behind the scenes, right?
Exactly. It does all the heavy lifting, but it creates a really fragile environment.
Yeah, because the moment that Python script landed on a machine without a GPU to receive that PTX code, boom, it threw a hard runtime error.
Yep. The goal of the port was to tear down that fragile Python script and rebuild it entirely in C++ sign.
And they wanted to achieve two distinct things with that, right? C++ plus zero cost abstractions and compile time type safety.
That's right.
And here's where the mechanism, how these languages operate, gets really interesting to me. I mean, a lot of people compare Python to an automatic car and C++ to a manual race car.
Yeah, you hear that a lot.
But that just describes how they feel to drive. Let's look at how they actually manage a factory floor.
Okay, I like this analogy.
Right, so Python operates like a micromanager. Every time a worker goes to pull a lever, Python pauses production, checks their ID badge, verifies they have permission to pull the lever, and makes sure the lever still exists in memory.
Which is immense overhead.
Huge overhead. But C++ gives the workers the master blueprints on day one, locks the factory doors, and just assumes everyone knows their job perfectly so they can run at blinding speed.
What's fascinating here is that compile time type safety is basically the act of checking those blueprints before the factory even opens.
Right.
The C++ compiler verifies every single data structure, every memory allocation, every logic rule before the program ever executes.
Whereas Python tries to figure out if a part fits on the assembly line while the conveyor belt is already moving.
Exactly. And when we are dealing with thousands of individual GPU threads running simultaneous Monte Carlo simulations, Python's micromanagement, its automatic memory handling and garbage collection, it creates massive performance bottlenecks.
It's just too slow.
Yeah, C++ removes that middleman entirely. It offers bare metal predictability.
So no surprise delays.
None. There are no surprise delays because a garbage collector decided to pause your threads and clean up unused memory arrays mid-calculation.
Wow.
You dictate exactly how many bytes of memory are moving, where they are going, and when they will arrive.
But getting that absolute control introduces a pretty brutal architectural hurdle. Mixing standard C++ code for the CPU with specialized code for the GPU requires two entirely different compilers.
Oh, absolutely.
The developer used MSVC for the Windows CPU side and NVIDIA's specialized compiler, NVCC, for the graphics card. And these two compilers do not naturally speak the same language at all.
No, they don't. The project relies on a header-only template design.
Right.
So the MSVC compiler handles the template instantiation on the CPU side, while the actual heavy lifting math, the kernel body, lives in a separate .cop file destined for the GPU.
And the point of catastrophic failure between these two compilers is this wild concept called C++ plus name mangling.
Yes, name mangling is basically how compilers internally decorate function names to keep track of complex features.
So if you write a function called, say, calculate that takes an integer,
The compiler might secretly rename it calculate underscore I.
okay, and if it takes a float, it becomes calculate underscore off.
Exactly. This allows the compiler to tell them apart. But the big problem is that MSVC and NVCC use completely incompatible mangling dictionaries.
So it's like they're speaking two completely different dialects.
Yeah, MSVC might scramble the name into this crazy sequence of letters and numbers, while NVCC uses an entirely different symbol system. So when they try to link the program together at the end, they literally cannot find each other's functions.
That sounds like a nightmare.
Yeah.
So how did they fix it? The developer bridged this chasm using an extern C declaration, right?
They did. It basically acts as a primitive universal translator. It forces both compilers to drop their complex C++ name mangling entirely and revert to the basic universal standard of the C programming language.
Which has no concept of overloading or complex objects.
None at all.
And that introduces a massive restriction, doesn't it? Like absolutely no complex C++ objects are allowed to cross that boundary.
Nope.
You cannot pass a dynamic array or some sophisticated class structure over an extern C bridge.
Yeah.
The only vocabulary allowed across the chasm consists of flat, raw pointers. We're talking about basic memory addresses like int pointer, float pointer, and unsigned long pointer.
Right. The communication is dumbed down to simply pointing at a specific block of memory and saying, hey, the numbers start here.
Wow.
And because the communication is reduced to its most primitive state, error handling becomes incredibly rigid. Well, the modern C++ standard allows you to elegantly return complex error objects like a vector detailing exactly what went wrong. The extern C bridge cannot physically handle that payload.
Which perfectly explains the ruthless error handling in the code.
Yeah.
The developer had to implement a standard exit1 command on any CUD errors. If the GPU encounters a problem, it doesn't send a polite error message back to the CPU. It just pulls the emergency brake and instantly kills the entire program.
It's brutal, but it works.
But if we look at the bigger picture, this forced primitive communication actually creates a brilliant architectural boundary.
How do you mean?
Well, it enforces a perfectly clean separation of concerns. The CPU is forced to handle all the complex logic, the memory allocation, the overall orchestration of the program. And the GPU is treated strictly as a dumb, blisteringly fast number crunching engine.
Oh, I see. Yeah.
And it just receives a raw pointer, executes the massive parallel math, and hands the raw results back without ever getting tangled in complex object definitions.
That's a great point. But, writing the code and building that raw pointer bridge is often the easiest part of the job.
Wait, really?
Oh, yeah. Automating the compilation so that other developers can actually download the code and run it on completely different machines without everything shattering. That brings us to a concept called build system dualism.
Ah, right. Because to prove the robustness of this C++ port, the developer actually built the project using two completely distinct build systems side by side, CMake and XMake.
And the comparison paints a really stark picture of modern software engineering.
Yeah, CMake proved to be a grueling battle. The developer had to manually fix 6 separate bugs just to get the project compiling.
It was a mess. The core issue was CMake's built-in CUDA language support actively clashing with MSVC's flag inheritance.
And flags are basically the specific rule sets passed down to the compiler instructing you how to behave.
Yeah,
right? Visual Studio's CUDA flag inheritance was so fundamentally broken that the developer had to completely bypass it. They used an add custom command to explicitly invoke the NVCC GPU compiler directly, literally manually wiring the two build pipelines together.
Yeah, and on top of that, they had to fight a total war over CRT flags, specifically MT versus MD.
Okay, explain MT versus MD for us.
So the C runtime library, the foundational code that handles basic tasks like memory allocation, it can be integrated in 2 ways.
Okay.
MT stands for multi-threaded static, meaning the library is physically baked directly into the final executable.
Okay.
MD stands for multi-threaded DLL, meaning the program relies on an external dynamic library loaded by Windows.
So if MSVC is compiling the CPU code expecting a static MT library, but CMake forces the NVCC compiler to expect a dynamic MD library,
then the two halves of your program will fundamentally disagree on how memory is allocated.
oh man.
Yeah, they will fight over the exact same memory space, and the program will crash before it even finishes booting up. The developer had to manually force CMake to align those CRT flags perfectly.
That sounds miserable. But contrast that grueling plumbing job with XMake.
Right, XMake was a breath of fresh air.
The XMake build system was vastly more elegant. It bypassed the rigid, broken rules and simply scanned the operating system's environment variables. By just looking for ostot gitten v CUDA path, XMake auto-detected the GPU compiler instantly.
Yeah, the configuration was minimal. The developer just invoked set languages C++ 23 and CD.
Which ensured the CDA compiler didn't accidentally override or downgrade the modern C++ standard being used for the CPU logic.
Exactly. The result was basically zero config on Windows. A developer could just clone the repository, type a simple command like xmake-j10, and it compiled perfectly on the first try.
That is incredibly satisfying. And it also provided a seamless solution for continuous integration, or CI.
Right, the CI servers.
When developers commit code, it gets sent to an automated CI server to be tested. And these servers rarely have dedicated graphics cards installed.
Right, which is exactly the scenario where the original Python script would throw a fatal error and crash the entire testing pipeline.
Yep. But in the XMake setup, the developer utilized a fine-packaged CUDA toolkit quiet command. And the crucial element there is the word quiet.
Because when the CI server boots up the code and fails to locate a GPU, it doesn't panic.
Exactly. It silently skips compiling the CDA blocks and gracefully falls back to a CPU-only version of the algorithm.
But wait, this raises a massive question for me.
What's that?
If XMake is zero config, works flawlessly on the first try, handles the CI server fallback silently, and requires a fraction of the code to manage, why did the developer spend hours fighting a prolonged battle with CMake and its 6 structural bugs? Why even bother building the project twice?
That's industry inertia for you.
Ah.
CMake is a legacy behemoth. It is the foundational plumbing that almost every major corporate repository and enterprise-level open-source project relies on.
So you basically have to use it. Yeah. If you write a highly optimized network algorithm and you want it integrated into a massive tech company's infrastructure, it absolutely must support CMake, regardless of how clunky or outdated the syntax is.
Building both just proves the code is battle-tested for ancient corporate pipelines, while actively embracing the streamlined efficiency of modern tools.
Precisely.
So let's look at the final score of this entire engineering feat. The developer took a black box Python script and rebuilt it in about 515 lines of raw C++ code spread across just 3 files.
And in those 515 lines, they achieved full mathematical feature parity with the Python baseline.
Amazing.
They verified the GPU kernel launched flawlessly, confirmed the silent CPU fallback worked on unequipped machines, and passed 34 total tests across both build systems.
Including 6 tests specifically hammering the GPU parallel threads.
Exactly. And I think for anyone listening, whether you're managing a massive corporate network, scaling a data science operation, or just trying to understand the physical realities of the software stack you rely on daily, this breakdown highlights a fundamental truth about performance.
Yeah, that high-level languages like Python get the headlines because they are fast to write and easy to read, but the actual horsepower required to process staggering amounts of data relies entirely on gritty, precise engineering down at the compiler level.
It relies on developers who are actually willing to strip away the abstractions, navigate those incompatible compiler dictionaries, and build those primitive raw pointer bridges between the CPU and the GPU.
So what does this all mean? We started this deep dive by looking at code that shattered the moment it hit an unexpected hardware environment. Python hid the complexity right up until it couldn't anymore.
Yeah, the physical reality of hardware eventually forces you to speak the primitive language of the machine if you want maximum efficiency and stability.
It really does. And it leaves me with this final thought for you to ponder today. If a mere 515-line C++ port can unlock this much predictable efficiency, speed, and safety for a single network algorithm just by bypassing Python's automatic overhead, how many other supposedly solved problems and bottlenecks in the world's global data science pipelines are currently running at a fraction of their potential speed?
It makes you wonder.
How many massive corporate servers are out there burning excess energy and compute time, simply waiting for someone brave enough to build a messy, brilliant bridge back to the bare metal?